We're going to work on creating a graph of a sinusoidal function from an equation, creating graphs from sinusoidal functions. So suppose a Ferris wheel has a height modeled by this equation. So height is equal to this equation, and we'll say x is degrees rotated around the Ferris wheel. So we know we're going to have a Ferris wheel, and a Ferris wheel is essentially a big circle. I'm actually not going to use that one. I'm going to start from somewhere nice here. Let's start from here so I know this is the center. Okay, we'll go all the way there. Great, so I know that's the center of our Ferris wheel. I need to find out a whole bunch of information about it. We don't know where it starts, where it goes, all of that stuff. So we're going to graph the relationship of it. So we know this is a sine wave. So we're going to say to go around the Ferris wheel, it takes 360 degrees. We'll say this is a measure of degree. That makes sense because it's a complete circle. So what we need to do is we need to build a graph of a proper scale. They've given us some of the information. And if you remember a function for a sine graph, it's equal to a sine x minus h, I think is the letter they'll use for you guys. And then plus k, are those the letters you guys are used to using? I think so. Yeah, okay. So we're going to talk about what each of these do. K talks about a transformation vertically up or down. Okay. H talks about a transformation horizontally left or right. And A talks about stretching and compressing and flipping. Okay. They all give us a lot of information. Okay. Because from a normal sine wave, and that's what we're going to kind of do. We're going to start with a normal sine wave. We'll put a normal sine wave here. Normal sine wave, we usually have values like 90, 180, 270, 360. Right? And a normal sine wave, goes up. I'm going to need to make this go up by 3s, I think. 2, 4, 6, 8, 10. Yeah, so I'm going to go by 3. Which will be a bit tough. 3, 6, 9, 12, and 15. That should do it for us. Okay, a normal sine wave starts at the origin, which is 0, 0. Okay, and it actually only goes up to 1. Okay, so normally we go up to a point, but technically it only goes up to 1. Then it goes down to 180 and 0, then 270 and -1, and 360 and 0. So the normal wave would look, for sine, something like this in comparison. And because of our scale, it looks really, really flat. Okay. The equation of the axis of our normal wave, let's change the color, it would be actually 0. It runs right through the middle of it. Well, our k value tells us how far to move the equation of the axis. Because it's plus 7, it's telling us to move the equation of the axis up 7 units. So our new equation of the axis, okay, the new middle of this function, should be, I'll do it in green, at positive 7. So that would be about here in terms of what we're doing. Oh, that's a good arrow idea. So we've now shifted the whole function up. Okay. So if you were to draw the new one with these ideas, it'd be like that. It'd go up to, start at 7, goes up to about 8. 180 comes down. Then it would be back at 6. And then 360 is about here, back here. So this is what our wave looks like right now. Okay, so we're drawing the transformations. The only thing we've applied is the k. The k is the only thing we've applied. It'll be easiest if we kind of do A next. I should have really actually done it first, but I want to do it next just because of the scale I have. What we do with the A is we take those 1 values and we pull them. And this says we need to pull it 6 units, okay? So from the original, if we had done that, it would go up to the unit 6, come down, and then go down to -6, okay? It would have been easier if I actually done that first. So I'm going to actually regroup. I'm going to do that first and then apply it to the next one, just because I think it would have been simpler. So because we take all of our y values, so I'll write these coordinates out. This is 90 and 1. This is 180 and 0. This is 270 and -1, and this is 360 and 0, okay? To apply your amplitude or your A value, this is 0, 0. You just multiply it by whatever the A value is. So 0 times 6, well, it stays at 0. This value doesn't change. 1 times 6 becomes 6. So our new height is at 6, so the wave jumps way up here. 0 times 6 is 0, so it comes all the way back down. -1 times 6 goes down to -6. This would be -3. This would be -6, so it goes way down here. Okay, so it's stretched immensely. And then 0 times 6 is 0 again, so we come back up. So that was the original stretch. The equation was the same in this one. So now we'd have to move this stretched guy. We'd have to move it up 7 units. So we know that the distance is 6 from the equation of the axis. So because the equation of the axis is at 7, we got to go up to the number 13 here. Okay, I know on our scale it's not easy to see. That also means, because our equation's at 7, it goes all the way down to the value of 1. So maybe I'll use a different color now to differentiate. Down to 1, back to the, oops, sorry, this would be the middle. This would be down to 1, and that would be there. So now our stretch goes up 6 units, back to the middle, down 6 units, and back up again. Okay? And then that's our H check. So we, or no, sorry, not our H, that's our A. The last thing we do is our H. So this says positive 90. But positive 90 is actually moving something in the negative direction. So we're going to move it to the left 90 degrees. So we take each of these values, each of their x values, okay, and we shift them to the left 90 degrees. So this one that's at 0, it's at 0, 7. That's the coordinate technically, 0, 7. It's now should be at, and I know our wheel kind of got in the way, but it should be at negative 90 and 7, okay? It doesn't work out great, our wheel's in the way. This one here though, 90 subtract 90 is 0, so it goes back here, okay? So it's now shifted 90 units in a negative direction. Same with this one. It shifts 90 units in a negative direction. Okay. This one shifts 90 units in the negative direction. This one shifts 90 units in a negative direction. I guess we'll draw it in black because that's the only color I don't have going right now. So it comes up, goes down, down, up, and then the pattern would continue back up to 13 here. So the black one is kind of our finished one. So it looks like we get on the Ferris wheel at the highest point, which is really odd. So if we were to apply this information to the Ferris wheel, we actually start up here, okay, and then we come down. The equation of the axis is the middle of the Ferris wheel. So the equation of the axis is at 7. So this Ferris wheel is 7 meters above the ground. The radius of the wheel is the amplitude, and we know the amplitude is 6. So we know the radius from here to here is 6 meters, or from here to here. 6 meters, still the same thing, it's still a radius. The lowest point is 1 meter above the ground. The highest point is 13 meters above the ground. And we know it takes 360 degrees to rotate all the way around this Ferris wheel, okay? We can use, I know this was really messy over here, but we can use kind of our graphing calculator here. I need to change it to degrees, and that means these need to be nicer values. Let's put this actually at 0. And actually 360. Okay, so let's use our graphing calculator. Y can be at -1 and 15. There we go. Okay, so 6 sine x minus 90. What do we say, plus 7?
Yep.
Okay, so here's our Ferris wheel. Oh, sorry, plus 90, right?
Yep.
There we go. We take a look at it, our starting point's 0, 13. At 90 degrees, I just want to find out what the coordinate is at 90. So at 90, we said we were going to be at 7, I believe. Yeah, and that falls right on our Ferris wheel here. Our other minimum value, zoom out a little, is 180 and 1. We have another value here. In the equation of the axis, we also said y was equal to 7. It runs right through the middle. And that's exactly where those major points were, right? So 0, 13. After 90 degree rotation, we're 7 meters in the air. After 180 degrees, we're 1 meter from the ground. After 270 degrees, we're 7 meters up again, and we end at 13. Somehow we get on and off at the top of this Ferris wheel, which is ridiculous. It's super high, but that's the idea. Verify, I think that, oh, and the one other thing is they want us to estimate at 200. Well, we don't really need to estimate at 200. I can take this equation, okay, so the height of the Ferris wheel is equal to, and actually, we're trying to find when x is the value of 200. So we go 6 sine x is 200 plus 90. Oops. And what do we say? Plus 7, I think it was? Yeah. And we can just literally work it out. So we get 6 sine 290 plus 7. So we find out what sine 290 is, and then times 6, and then add 7. So we'll do all those steps on a calculator. Sine 290, okay, is equal to that value times 6, and then plus 7 equals 1.36. So apparently, after a 200-degree rotation, we are 1.36 meters above the ground. In a 200-degree rotation, remember this was to go from here all the way around to here was 180 degrees. Okay, to go up to here would be 270. So a 200-degree rotation is probably somewhere around here. That makes sense, 1.36 meters. And we can verify it by actually, if I say x is equal to 200, you can see that point of intersection. Yeah, and they rounded it to 1.4. So that's exactly where that value was.